Today's video is on how to do the graphical discrete convolution, popularly called as reflect and shift convolution sum evaluation. What is discrete convolution? Already we had been seeing that the expression of discrete convolution is given as y of n is equal to summation k equal to minus infinity to plus infinity x of k into h of n minus k. This has also been considered with examples how to obtain the discrete convolution. In this case, we are going to do a graphical implementation for the discrete convolution. What is that is required? We would generate and implement this particular expression. We would see what is the procedure for it, and let us go on with our first example given by u of n convolute u of n minus 3. Why is one of them given in red, the other one given in blue? X of k represents a signal which is not going to be shifted. Hence, u of n minus 3 is chosen as a signal which would not be shifted, and h of n minus k is the shifted signal, which is easier to shift is the signal u of n. Hence, u of n would be shifted, or it is chosen for h of n minus k. In order to understand the video, it would be better to keep on drawing the various steps. Hence, a notebook and paper with pen would be necessary to understand the video fully. Let us consider the procedure that is used for implementing reflect and shift convolution sum evaluation, popularly known as the graphical discrete convolution. The first step, as has been given, is sketch x of k as a function of k. Considering the example of u of n convolute u of n minus 3, u of n minus 3 is chosen as x of k, and it is sketched here. Starting from 3, we have it as u of n. So this is what is our x of k. Next is for h of n minus k, first reflect h of k about k equal to 0, giving h of minus k. In the problem, u of n is chosen as h of n minus k. Hence, what is obtained here is u of n is flipped about 0, resulting in h of minus k, as has been given in step 2. Next, we go on to shift h of minus k to a large negative axis of n, thereby resulting in an example like this. Only up to minus 5 is shown. However, it could go even up to a large value of n. Next, we need to evaluate the mathematical expression for convolution, which is the product of x of k and h of n minus k, and an intermediate signal called as wnk is introduced, which is going to be equivalent to identifying at what interval the value of wnk changes. That is necessary. Hence, this variable has been introduced. Next, let us try to slide h of n minus k to the right till the mathematical expression of wnk changes, which means this signal needs to be shifted to 4, 3, 2, so on. At each stage, when we evaluate the value of w 3 of k, minus 3 of k, minus 2 of k, etc., we would see the result is 0, because the product of a signal which is at 3 and another product which is at minus 5 or at minus 4 or at minus 3 is known to be 0. Let us go on to consider the remaining steps that are involved in implementing graphical discrete convolution. In each interval of time shift, let us sum all the values of w and k to get y of n for that particular interval. Next, let us identify the value of n at which w and k changes. This is highly important because this marks the beginning of a new interval and tells us that the present time interval n is over. we need to repeat steps 5 to 8 till all the time shift and their respective mathematical expression for W and K are identified. N needs to be a large positive number. Formulate the expressions for y of n in terms of various n, giving a generic solution. Let us go on to the first problem. U of n convolute U of n minus 3 in a more elaborate way. U of n minus 3 has been sketched here as x of k, and it starts from 3 and it goes on for a large value of n, giving x of k. The second step is in generating h of minus k, which is a flipped version of u of n. Under a normal case, u of n would start from n equal to 0 and it would continue like this for a large n. A flipped version means it starts from 0, minus 1, minus 2, so on for a large n. The third step is in generating h of n minus k, which means shifting n to a large negative value. Here only up to minus 5 has been shown, and thus we have shown for a shift up to 5. Now let us try to evaluate the product of, or the convolution of, x of k and h of n minus k. Since one signal exists at 3 and another signal exists at minus 5, the product of such a signal would be 0, as has been seen here. Wn of k would be 0. Next, let us go on to keep on shifting this particular signal, and during our shift, let us keep shifting this signal. First, it would move and it would be at 1. Again, we are shifting one more step and we are going to move it at, so that it lies as 2, as is shown here. It is going to lie at 2. Now, what is the value of W of n of k? Here, when we see W of n of k, at both cases is 0, which means this will remain so till n is less than 3. Let us try to just move a step forward. When we try to move a step forward, we would see that this red signal is going to lie over the blue signal, which means we have come to the end of the current interval, which means it is at n equal to 2. Written as n less than 3, the value of y of n is going to be equal to 0. Now let us go on to see what would be the other cases. Till the sliding of h of n minus k till 2 was discussed in the previous slide. Now what we are going to consider is, we are going to take h of n minus k a step forward and obtain it as h of 3 minus k. So it lies over x of k, which starts from 3, and the product of w n k is 1, as has been shown here. Next, let us go a step forward by sliding this one more step, thereby making it lie over 4. So it is going to be at 4 and 3, we are going to get a product, which means we have w4 of k and we have w3 of k, and as has been mentioned in our previous case, wk is going to be the summation of w3 of k and w4 of k. Thereby this is going to be 1, this is also going to be 1. So sum of these two is going to be 2 at 4. So let us now try to generalize with this particular values that we have got, that is, at n equal to 3 the value of y of n is 1, at n equal to 4 the value of y of n is 2. So how can we write the value of y of n in a generic case? We could write it as, if n is equal to 3, it is 3 minus 2, so it is 1. When n is equal to 4, it is 4 minus 2, so it is equal to 2, which means for any value of n greater than or equal to 3, the solution of the sum of y of n is given by the expression y of n minus 2. What happens to the value of y of n before 3? That has already been evaluated, and it has been given that the value of y of n would be equal to 0 when n is less than 3. So this completes the first problem on the graphical discrete convolution. Let us go on to a slightly improved version of a problem wherein we are going to consider that the problem is beta n into u of n convolute u of n minus 3. Let us try to sketch the two signals. As before, x of k would be u of n minus 3 and h of k would be beta n u of n. So, u of n minus 3, as in the previous case, starts from n equal to 3 and it has been sketched to be having an amplitude of 1 up to, of course it has been shown only up to 7, but the signal could continue as is known for the step signal. Next, what do we do for beta n u of n? Beta is assumed to be less than 1, which means we need to consider beta to be, say, 0.9. So, when 0.9 is at n equal to 0, the value would be 1. At n equal to 2, it would be 0.81. Thereby, we would get a signal like this, which is flipped with h of minus k being shown here. Though it is not drawn to scale, the shape would appear almost like this. Next, what are we supposed to do? As before, we need to shift h of minus k to a large negative value to generate h of n minus k. This has been done by shifting the signal from 0. It has been shown here only till 2, otherwise the signal may move out of the screen, and at any large value of n, even if we start the signal here, our main aim is what would be the value of Wn of k. We know that even at this stage, the two signals lie apart, there is no overlap, and hence the value of x of k into h of minus 2 minus k or any other value would remain at 0, thereby giving us that for this particular case, the Wnk value, that is W minus 2 of k, would also be equal to 0. Please note that this is an instant by instant value. W minus 2 of k, W minus 3 of k, minus 4 of k, etc. is what is generated in the value of W. Next, let us try to go on for the next stage when n minus 3 is less than 0, which means n is less than 3. We had already considered the case where it was at 2, that is minus 2. Now we are trying to slide this signal so that this signal lies at 2. Hence, now what we get is when h of 2 minus k is there and here we have x of k, still what would be the value of Wn of k? That is W2 of k, still it would be 0 because both of them are not having any overlap, or in other words, there is a gap between the two signals. One signal is lying here, the other one is here. A product of such a case would be 0 and hence W2 of k would also be 0. So what is the conclusion that we have got? We say that, can we conclude? Let us just attempt. Before concluding, let us try to shift this over 3. When we shift it over 3, we know that the value of W3k is not equal to 0. So we have identified n, which is going to be the end of the current interval, and we have also identified that from 3 onwards there is going to be a change in Wn of k. So we can conclude that 2 marks the end of the present value and 3 marks the beginning of the new Wnk. Hence, we can conclude by saying y of n is going to be equal to 0 for n less than 3. Let us consider the problem beta of n u of n convolute u power u into n minus 3 when beta is less than 1 for n is equal to 3. Hence, h of 3 minus k makes the signal to be such that it is having a value here giving a product of W3 of 3, which would be evaluated later. Similarly, let us now try to shift the signal by one value, thereby giving us as W4 of 4 and W3 of 4. Y of 4 would be a summation of W3 of 4 and W4 of 4, as has been mentioned in the procedure slide. Also, we need to evaluate what are these values. We have just said that a product has been generated with h of 3 minus k and x of k, or with w3 of 4 and w4 of 4. Let us go on to see how the evaluation takes place. We recall that the geometric progression is given by k equal to 0, n minus 1 summation ak is 1 minus a power n divided by 1 minus a. On similar grounds, for this particular case, we would be getting the summation as 1 minus beta power n minus 2 divided by 1 minus beta for n greater than or equal to 3. n minus 2 has been generated because it starts from 3 onwards. And already the value of y of n for n less than 3 has been evaluated, and it has been shown to be 0, giving the solution y of n equal to 0 when n is less than 3, and y of n is equal to 1 minus beta power n minus 2 divided by 1 minus beta when n is greater than or equal to 3. One extra problem is given for your implementation. The problem is y of n is going to be equal to u of n plus 3 convolution u of n minus 3. The solution is for n less than 0, y of n is going to be 0, and for n greater than 0, y of n is going to be n plus 1. Thus, the solution has been summarized here. More complicated problems could also be worked out in order to understand the concept of graphical discrete convolution. So we go on to the references. Simon Haken is the textbook which has been used for obtaining the procedure of graphical discrete convolution.